Hello everyone. So, this is lecture 5 in the 4th week of this course. So, please recall that in the previous lecture we were learning about the Fletcher-Reeves form of conjugate gradient algorithm, right. So, in conjugate gradient algorithm we need to choose n vectors given a quadratic function to minimize, we need to choose n vectors d0, d1 dot 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 dn minus 1 in such a way that they are H conjugate. What is H conjugate? They should satisfy the condition that dA transpose H dj equal to 0 when I not equal to j, right. So, we were so the question now is how, given a positive definite matrix H, how do you choose these directions d0, d1 dot 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 dn minus 1. Okay. So, in the previous lecture we derived a formula, right. So, please look at this part where we the first one is very clear, d0 is just minus g0, right, which is exactly the same as the negative of the gradient of f at x naught, but from then on. So, here it just says beta naught, beta 1 and all that, right. So, the final formula actually gives you how to choose the rest. So, when d0 is minus g0, right, d1 is, so if d0 is minus g0, then d1 is minus g1 plus g1 transpose g1 by g0 transpose g0 d0, and d2 is minus g2 plus g2 transpose g2 by g1 transpose g1 d1, and so on until dn minus 1 is minus gn minus 1 plus gn minus 1 transpose gn minus 1 by gn minus 2 transpose gn minus 2 d n minus 2. So, write this properly as d1. Okay. Yeah. So, this is basically Fletcher-Reeves algorithm. Okay. So, recall that we this is the full algorithm, right. So, where you initialize x naught tolerance k equal to 0 while norm g k greater than the tolerance, right. So, this step changes. Okay. So, you are not going to just choose dk equal to minus gk blindly, okay. You are going to choose dk in a slightly different way, okay. But otherwise everything is the same, you choose alpha k by, actually since it is a quadratic function you choose by exact line search algorithm, then xk plus 1 equal to xk plus alpha k dk and k equal to k plus 1. Maybe I will write this in a fresh page. So, this is the conjugate gradient algorithm as given by Fletcher-Reeves. Okay. So, of course, you initialize x naught tolerance and k equal to 0, and while norm g k greater than the tolerance. So, what do? You first choose, in the at least in the first step you choose, okay. First I will write this as this as well. So, you choose d0 as minus g0 since that is the first step, okay. So, you can choose alpha k such that alpha k by exact line search algorithm. So, I will write that as minus gk transpose dk by dk transpose h dk, right. So, and then we have xk plus 1 equals xk plus alpha k dk, okay. And here you can actually find dk plus 1. What is that? it is minus g k plus 1. So, minus g k plus 1 can be found because you know x k plus 1 from the previous step, right, and plus g k g k plus 1 transpose g k plus 1 by g k transpose g k into d k. Okay. So, this is the extra step that we are actually going to choose the direction for the next iteration, okay, here itself, and here you can actually write k equal to k plus 1. Okay. So, and finally, you output x star equal to x k. Okay. So, we will actually implement this algorithm in Python. Okay. So, what I have so I mean before that we will I mean what I claim is that, so when you use this algorithm, right, so for any h positive definite, right, for you are given a quadratic function and h is positive definite. Okay. I claim that the solution is attained in at most n steps. Okay. So, we will verify that. So, what we are going to do is we are going to give some h which are of higher dimension. Okay. So, we are mostly working with 2 cross 2 and maximum 3 cross 3 matrices, right. So, we will now work with a 5 cross 5 matrix. Okay. So, and we will verify, we will just write down this algorithm in Python and verify if we attain the answer in at most 5 steps. Okay. So, I am going to generate arbitrary 5 cross 5 positive definite matrices, right. So, so first there are 2 problems here. First is arbitrary, that means I mean I need to randomize, right, I am not going to give you a matrix and say that it works for this matrix, right. So, I am going to generate an arbitrary matrix that has to so that is the first issue, how do you generate that, and the second is how do you ensure that it is symmetric and positive definite, right. So, for the second question I will just write down something. Okay. So, let us say I take some arbitrary matrix, okay, which has arbitrary elements which need not be symmetric, which need not be positive definite. Okay. So, let me call it A. For an arbitrary matrix A, we have A transpose plus I is positive definite, symmetric and positive definite in fact. So, symmetric I think you can see very clearly because A transpose is symmetric and I is also symmetric. So, when you add 2 symmetric matrices the answer is symmetric as well, right. So, symmetric is not a problem. So, but why is this positive definite, right. So, for recall that the proof is just one line. So, I can write that down. Recall that if x transpose h x is greater than or equal to 0. So, a matrix H is positive definite if and only if x transpose h is greater than 0 for all x not equal to 0, right. So, let us do this here. So, x transpose A transpose x plus x transpose I x is just x transpose x is x transpose A, sorry that is A transpose x, A transpose x transpose A transpose x plus x transpose x, right. So, if x is non-zero, this is greater than 0, right, and yeah. So, this is anyway greater than or equal to 0, because you are I mean taking the norm squared of the vector A transpose x, right. So, very clearly this is greater than 0 for all x not equal to 0. Okay. So, that is the reason I said A transpose I is positive symmetric and positive definite. Okay. So, that is what we are going to do. We are going to generate a random matrix A, okay, and going to do an A transpose plus I. So, we will generate a positive definite matrix. Okay. So, now the question is, how do you generate this so called random matrix, right, where A, right. So, you could have seen a part of this in the last lecture also, okay, where I mean used something called as rand function, right. So, in some of the earlier lectures we used something called as the rand functions and so on. Okay. I will give you, I will spend a few minutes, maybe 3 to 4 minutes explaining what those random the commands rand, randent and all of them are. Okay. So, let me first import numpy, which is very important for defining these commands. Okay. So, I will first introduce this command called rand. Okay. So, let us say A equals np dot random dot rand of 100. Okay. So, what does this do? It generates a random variable, okay, that is uniformly distributed in the interval 0, 1. Okay. np dot random dot rand, that command generates a random variable that is uniformly distributed in the interval 0, 1. So, I will first generate one random variable just to show you how it looks. Okay. Oh, okay, I haven't printed, I am sorry. So, okay, so that is 0.724. Okay. So, I will just do it 3-4 times 0.022, 0.656, 0.098 and so on. Okay. So, what this does is generate a random variable that is uniformly distributed in the interval 0, 1. Okay. So, yeah, it generates a real number in between 0, 1 and the distribution is uniform. How do you check that? So, I will generate like 1,000,000 variables. Okay. So, and yeah, printing 1,000,000 variables is not a good idea. Okay. So, instead what I will do is print the mean and median. Okay. Sorry, median. So, you know that the answers are 0.5 and 0.5, you will see that the answers here are roughly 0.5 and 0.5 as well, and there you go, right. Yeah. So, if you are still not convinced, I will even plot the histogram. Okay. So, that needs matplotlib dot pyplot. Yeah. So, fine, and I will plot histogram. So, yeah, this is not going to be used anywhere. Okay. So, I mean if you if you are not learning this, it does not matter, I mean at least for this course. Okay. This is just to prove to you that what is being generated is a uniform random variable. Okay. Yes. So, you can see that yeah, so the density will be 1, right. So, for 0 to 1 the yeah the density is supposed to be flat at 1, it is not exactly flat, it is a little bit here and there, but that is expected, right. So, yeah, if 1,000,000 is increased further, even this will I mean this will be minimized even further, okay. So, yeah, that is it is so simple as this, okay. So, now you should be asking, so what if I want to generate a random variable which is uniform in some other interval, say uniform in a comma b, okay, or say uniform in -10 to 6 for example, okay. So, you can convert this, right. For example, if you want it to be uniform in a comma b, right. So, you can do it this way, you use the command a plus b minus a into np dot random dot rand of whatever the number you want, let us say num, okay. So, and why does this work? Because so when you use b minus a into this, so you expand this as uniform 0 comma b minus a, and when you add a it becomes uniform a comma b, right. So, that is basically the reason. So, yeah, you can easily do this by just using the command a plus b minus a into np dot random dot rand of the number, okay. So, that is fine, and you can also generate matrices, okay. So, that is again for your reference. So, suppose I want to generate a 5 cross 5 matrix, okay. So, you just do this, and yeah, of course, I should have printed it, I am sorry. Yeah, so you have a 5 cross 5 matrix, each of these elements are generated uniformly in the interval 0 comma 1, of course they are independent as well, they are independent picks of uniform 0 comma 1 random variables, okay. So, this is how you generate uniform random variables, and how do you generate a Gaussian random variable, right. So, that is very simple, instead of np dot random dot rand, just make it np dot random dot rand n, okay, n is for normal, okay. So, when you do this, so this actually generates okay, so maybe I will yeah. So, if you write rand n, then it generates a random variable which is n of 0 comma 1. So, mean 0 and variance 1, okay. So, how do you generate n of mu comma sigma squared? Very simple, you just write it as mu plus sigma into np dot random dot rand n of 5 comma 5, okay, as simple as that. So, I will, you can see this generation, I mean the latest one is printed. So, you can see negative values, you can also see rarely 1.5, 1.7, minus 1.18 and all that. So, it is a 5 cross 5 which is uniform, sorry, which is Gaussian with 0 mean and variance 1, okay. So, here again you need not believe me, you can generate this yeah 1,000,000 times and print the mean, median and the variance here, okay, and the histogram as well, yeah. So, you can see that mean and median are close to 0 and the variance is close to 1. So, this if you are not convinced, you can increase the number of bins, I will increase it to 100 just to show you how nicely it looks, yeah. So, now you can see the beautiful bell curve, right, yeah. So, that is for rand n is for Gaussian random variables, okay. And finally, I also want to introduce to you another command, okay, which is randint. I think I introduced it in the last class. So, let me do it again for completeness. Okay. So, suppose I write this and the number. So, I will generate a 5 cross 5 matrix again for you. So, what this does is it generates random integers uniformly in -9, -8, dot 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 8, 9. Okay. The last 10 is not included, please understand that. Okay. So, it will pick integers uniformly in -9, -8, dot 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 9. Okay. So, here again so since we are just generating 5 comma 5, I will just print this for once. So, you can see that it is a 5 cross 5 matrix which has values from -9 to 9, okay, distributed. And if you want me to plot the histogram, so let me generate 1,000,000, and you can see that the numbers are almost equal, right. So, that is randint. So, I have just defined 3 commands, okay, rand for uniform distribution, randn for Gaussian distribution, randint for random integers uniformly in between the first point and the last point that you actually specify. Okay. So, we will use these and generate H matrix, that is basically why, I mean that is my motive finally. Okay. So, A is np dot random dot randint, randint from -9 to 10, and let me generate a 5 cross 5 matrix, okay, and let H be what I just defined, A into A transpose plus np dot I of 5, okay, and X also I will define in random. I will use a Gaussian random variable. So, since this is 5 dimensional, I need 5 values. Okay. Now, I will implement this particular algorithm. Okay. So, I need to I have initialized x0, tall I will just write it in the code 1e minus 6, and I have to initialize k equal to 0 and d0 equal to minus g0, right, and minus g0 is just minus h x naught, okay, nothing fancy. Okay. So, let me write k equal to 0 and d is minus h x, okay, since I have not defined b. Okay. Now, while np dot linalg dot norm of h x is greater than 1e minus 6. Okay. So, the first step is to choose alpha, then to update xk, right. So, so alpha is just minus gk transpose hk, sorry, minus gk transpose dk, and gk is hx, right. So, alpha is minus d dot hx by d dot hd, okay, and so one thing is I cannot straight away update xk plus 1 because I need xk here, right. So, what I will do is I will define something called x old as x, okay, and then update x, okay, x plus alpha into d, and I will also update d now. D is minus h at x, this is the new h, okay, that is gk plus 1, this is minus gk plus 1, and here it is the new x and here is the old x. Okay. So, we will just write it that way, h at x dot h at x by h at x old dot h at x old into d. Okay. So, I have updated d and I will also write k equal to k plus 1. Okay. So, I have not written the print statements. So, I will write that here, print percentage d, percentage 1.3 percentage 1.3 e, percentage 1.3 e. I have tried it 5 times. So, do not be wondering why am I writing so many times. So, this is k x of 0, x of 1, x of 2, x of 3, x of 4 and np dot linealg dot norm of h at x. Okay. So, that is for the first, that 0th iteration rather. So, for the other iterations I will print them here. Okay. So, let us see, okay, I have written the spelling is wrong here, sorry about that. Yes. So, note that I have actually generated H to be an arbitrary 5 cross 5 symmetric positive definite matrix, and I have generated the initial point to be an arbitrary point as well, but nevertheless we have got the solution in just 5 iterations because n is equal to 5. You can try this with any n as well, I mean, so you can try with maybe 12, 15 whatever. Okay. So, just that, I mean, you have to change the print statement, be careful with that, but otherwise the number of iterations is just going to be n or even lesser than that, I mean that is also possible. Okay. So, yeah, that is the good thing about the Fletcher-Reeves algorithm that we just learnt now. Okay. The question now should be, how do you generalize this conjugate gradient algorithm, that is the Fletcher-Reeves part of conjugate gradient algorithm, to any function, right. So, yeah, for quadratic function even without this you can find it using H inverse b, right, sorry, minus H inverse b, right. So, that is correct. So, how do you generalize this to yeah, general functions if you want to minimize some other function which is not quadratic, right. So, you can use a very similar algorithm. Okay. It will be a little bit faster than gradient descent anyway, but it may not be too fast because I mean the matrix H is actually changing continuously, right. So, I will write down the algorithm anyway. Okay. So, this is so what I have written here is for minimizing quadratic functions. So, this is when f is a quadratic function with its Hessian positive definite. Okay. So, yeah, so what if it is not? So, the algorithm is just a small modification of what we have here. Okay. So, yeah, so this is Fletcher-Reeves for general functions. So, that is just, yeah, initialize is the same, x naught tolerance k equal to 0 and d 0 is minus g 0, do all that, no issues. and while norm gk is greater than tolerance. Okay. So, choose alpha k by backtracking line search possibly, because yeah, for other functions we usually use backtracking line search algorithm, and x k plus 1 is x k plus alpha k dk. Okay. And here is a catch. Okay. dk plus 1 is minus gk plus 1 plus gk plus 1 transpose gk plus 1 by gk transpose gk into dk, right, if mod of k comma n is not equal to 0. Okay. And if it is equal to 0, it is just dk plus 1, sorry, minus gk plus 1. Okay. So, this is a small modification. I mean, let me explain what this actually means. Okay. Because the other parts you might have expected it to happen. So, in general, I mean this part, this mod k comma n equal to 0 does not occur in a quadratic function, because I mean the answer completes in n minus 1 steps, right. So, at the nth step we do not go into the while loop. Okay. But for a general function we could have many iterations, right. So, at 0th iteration, first iteration dot 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 n minus 1th iteration. Okay. So, yeah, for 0th iteration you just use minus g0, that is fine, but for the first, second dot 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 n minus 1th you do as such what you saw in the previous page. Okay. But at the nth iteration, okay, you are kind of reversing the cycle, or I mean restarting the cycle, rather reversing is not the right word, restarting the cycle. Okay. So, at the nth iteration you do as you would do at the 0th iteration. Okay. Just choose d0 equal to minus g0, right. So, dn will be just equal to minus gn. Okay. And then from n to n plus 1 to 2n minus 1 you will use this part again, minus gk plus 1 plus dot dot dot, right, and at 2n you will again choose minus g 2n. Okay. d 2n will be minus g 2n. Okay. And so on. So, that is basically how Fletcher-Reeves works for general functions which are not quadratic. Okay. So, this completes the discussion for week 4. Okay. So, note that in the 3rd week and 4th week combined we have actually learnt the line search algorithms, both the exact line search algorithm and the backtracking line search algorithm, and as far as finding the directions are concerned, we have learnt the gradient descent or the steepest descent algorithm and the various forms of conjugate gradient algorithm, specifically the two forms, one is using eigenvectors and the other is using Fletcher-Reeves. Fletcher-Reeves is computationally efficient compared to the eigenvector formulation, and yeah, so but again eigenvector formulation works only when h remains constant for different iterations, but Fletcher-Reeves you can use even otherwise, right. So, Fletcher-Reeves form is preferred when you actually use conjugate gradient algorithm. Okay. So, in the next week we will actually start with Newton's method. Thank you.